Hello everyone, and here's another Physics 30 Alberta Diploma review question. This is the released item from 2009 and it's MC4. This is a simple linear momentum, so it'll be a conservation of momentum question. And here's the question. You've got two lab carts on a frictionless surface. Okay, so this frictionless surface tells us that we have an isolated system. We do not have to worry about friction. We do not have to worry about any external forces having an effect on our system at all. So we can go ahead and assume that conservation of momentum can be applied completely. The spring is attached in the middle right here. And when it's compressed, the string is then attached and then cut. So the cut string then allows the spring to exert a force on both carts. That force, of course, following Newton's third law, will be equal and opposite. So both of these carts will experience the same force from the spring. And we are asked to find the speed of cart 2 after this has happened. And we're told that there's a value for cart 1. So cart 1 has a 0.80 meters per second velocity to the left, and cart 2 has a velocity to the right that's unknown. The other thing that's known is a ratio of the masses. So if cart 1 has a mass m, cart 2 has a mass that's 2.5 of m. Okay, so that's going to come into play when we do our algebraic analysis. So let's go ahead. This is a fairly straightforward question. Hopefully you're familiar with linear momentum. If you're in my class, I'm going to get you to do a before and after analysis for pretty much everything. Just really helps visualize what's happening. And if we do a before and after, of course, we're going to take care of all of our masses, velocities, and momentums for each thing. So I'm just going to give these little annotations. M1, V1, P1, and then of course M2, V2, and P2. Well, at the beginning of this scenario, they're not moving; they're stationary. So this is nice and easy. Our velocity is 0, our momentum is 0 for each piece, and we're going to go ahead and put our algebra in here for mass 1, we're just going to call it m, and for mass 2, we're going to go ahead and call it 2.5 m. Okay. All right, so I've just cleaned that up a little bit, but importantly, what we're doing is we're just following this MVP analysis for each piece of this system. So our before system is stationary, it's not moving, so that means we're going to have 0 momentum for both of these carts. Afterwards, we're told that the velocity of cart 1 is 0.8. So I'm going to go ahead and put that in, 0.8 meters per second. And I know that's to the left, so I'm just going to make sure I keep track of that negative sign, because as usual, I'm going to call the left side of the page, I'm going to call that negative, and the right side of the page is going to be positive. Pretty conventional. Okay, so this velocity here is going to be a positive, because hopefully we can see it's going to be going this way. The question is by how much? Well, hopefully you can see this system here is now going to give me a value for the momentum. Okay, so let's go ahead and do that. We know that P is equal to mv. So all I have to do is multiply my velocity by my mass. Well, I don't know the value for the mass, so here we're just going to keep this as an algebraic expression. So I'm going to call this negative 0.8 m. That's all I know so far. Now, what's important here is that my momentum is conserved. So this piece here has to be equal to each other. In other words, the momentum before has to equal the momentum after. So I'm going to go ahead and just write that out as a statement. My initial momentum has to equal the sum of my final momentum. Well, if my initial momentum was 0, okay, because I have no velocity to begin with, if my initial momentum is 0, that means that my P1 and my P2 have to be equal to each other. See, I can rearrange this equation just to say that P2 is equal to P1. Okay, so these two are going to be equal to each other. Okay, so this is a really important statement. The fact that these two are the same links these two values here. So I can go ahead and put that in. I'm just going to write it out exactly the same. I'm going to say that P1 is negative 0.88 m, and that means that this P2 has to be 0.8 m also. Okay, I'm not going to worry about the negative sign for now. All right, I'm nearly there. One last little thing. I'm going to use this equation again. This equation tells me that V is equal to P over N. Okay, and now I can go ahead and put my values in that I already have, or at least my algebra. I know that 0.8 m, that's the momentum of P2. Let's do this for cart 2. So 0.8 m divided by the mass. Well, the mass is 2.5 m. Okay, hopefully you can see the masses cancel out. So I'm just left with 0.8 over 2.5. Now this is the fun part, because as usual in Physics 30, we actually have a situation where we don't really need to use a calculator. Okay, we can go, let's look at the possible solutions here. Well, 3.1, 2, 0.8, or 0.32. Well, it's not going to be 0.8, because that's a calculated value. So I can go ahead and eliminate that. It's not that one, cross that out. And we're dealing with 0.8 divided by 2.5. So it's not going to be A, because that's a big number. And it's not going to be B, because that's a big number too. So almost by elimination, we can see that we've got our answer. It's going to be D. And sure enough, if you go ahead and do the calculation, you get 0.32.